Okay, I think we can get started. Good morning, everyone. Welcome to the GIST Sea Level Rise seminar. We're very glad to have George Liu with us. He is a PhD candidate in the Department of Earth and Environmental Sciences at Columbia University, and he's affiliated with the Division of Marine and Polar Geophysics at the Lamont Doherty Earth Observatory. George's research is focused on understanding ice deformation, ice sheet stability, and glacial hydrology. And his research employs various methods from physical modeling to ice-penetrating radar measurements. George holds a Bachelor's of Applied Sciences, Applied Science in Engineering Science, with specialization in engineering physics from the University of Toronto, and is currently advised by Professor Jonathan Kingslake. Today, he will be speaking on the topic feedbacks between subglacial hydrology and ice sheet dynamics. So welcome, George.
Thank you, Patrick. All righty, so my screen should be up now. Hi everyone. Thanks for joining today, and thank you, Patrick, for the invitation and introduction. And since you mentioned Toronto, I'm just gonna pretend to be a baseball fan and say, "Go Blue Jays." Anyways, I'm George. I'm a PhD candidate at Columbia University, and today I'm going to be giving an overview on how subglacial hydrology and ice sheet dynamics interact. You can treat this talk more or less as a review of ice sheet modeling and subglacial hydrology topics that ultimately culminates with some coupled modeling work that I did at the beginning of my PhD. This work shown here today acknowledges the following for support in many forms, and it's also been published as a paper in 2024. So first, let's just establish the oft-repeated context given by ice sheet modelers, myself included. So here's a NASA figure illustrating the global mean sea level rise that has been observed over the last 30 years or so. And we see that it's gone up by 9 centimeters. Of that, 5 centimeters of it is explained due to additional water mass being added to the global oceans. And a lot of this additional water comes from ice sheets, primarily large ones in Greenland and Antarctica. Now, some additional context. Now from the IPCC, this is predicting future sea level rise until 2100. And while we see there's a lot of variability due to the different SSP forcing scenarios, one really big source of uncertainty is ice sheet instability processes. And this suggests that there's a lot of unknowns relating to ice sheet dynamics that leads to such a wide range of predictions. And to really drive this point home, these are results from an ice sheet model intercomparison project that was done in 2020 by Sarusi et al., ISMIP6, which predicts, this paper predicts the contribution of the Antarctic ice sheet to global mean sea level rise to the year 2100. And we can see that the range of predictions is pretty massive, varying by almost 2 meters. And some of these models predict mass gain rather than mass loss as well. And within these studies, even though they have the same forcing scenarios, there's significant variation in predicted ice sheet retreat and consequently mass loss. So where do these main sources of uncertainty come from? Here's just a schematic specifically, showing how ice sheets, specifically marine-terminating ice sheets, lose mass. And you're probably all familiar with this, so I'll just highlight some of the key sources of uncertainty as I walk through it. I'm particularly interested in the grounding line, which is where the basal water pressure equals the ice overburden pressure. Beyond that point, the ice is actually floating as an ice shelf. These ice shelves, they can provide backstress that help prevent further mass loss. And as they thin, calve, or disintegrate, those are all processes that carry their own uncertainties that I won't go into today. But as they thin and calve or disintegrate, that buttressing force weakens. And this could allow more ice to enter flotation, which increases mass loss at the grounding line and drives retreat. And one of the really big concerns that is flagged by the IPCC is when this retreat is happening on a retrograde slope. And that's because as the grounding line retreats inland and the bed deepens, the ice at the ground line becomes thicker, which increases flow speed and accelerates retreat. And this is a classic positive feedback loop that's referred to as the marine ice sheet instability. But it's really important to remember that these theories come from modeling work, and there's a lot of assumptions baked into these models. So beyond the uncertainties in how ice shelves behave, There's also uncertainties in how the ice is forced through various oceanic and atmospheric processes, which I'm sure a lot of folks here at GISS know a lot about. Um, but even so, there's a lot of intrinsic uncertainties in the dynamics of the ice sheet itself. So how it flows, how it interacts with the bed beneath it, and that broadly is what my thesis looks at. And today, as the title of my talk suggests, I'm interested in what's happening with the water below the ice. So next, I'm just going to give a quick overview of ice sheet modeling and use that as a background to highlight how water can influence the ice above it. So across long time scales, like years, ice behaves as a nonlinear viscous fluid, and this is represented by the full Stokes equations, which is a simplification of the Navier-Stokes equations. And these equations consist of a mass balance relationship relating the velocity gradients and a momentum balance relationship, the bottom three equations here. And this formulation relates the deviatoric stress tensor tau with the total stress tensor sigma. And these equations are relatively computationally complex to solve. And yeah, they're pretty complicated. There's uncertainty stemming in how we relate these stress tensors to the velocities. This is done through a relationship called Glenn's flow law, which I put on the left-hand side over here. So this is an empirically defined equation that describes ice deformation, relating the strain rate epsilon dot to the stress tau. It comes with many parameters that all carry quite a bit of uncertainty. Quite a few past GIST talks have been around these flow laws, I believe. Um, Notably, the exponent n, it's been the topic of debate. One of my chapters, though not this one, seeks to understand depth varying ice rheology further using radar observations. And I'd be happy to chat with people about that, but I digress. The strain rates, they're directly related to the velocity gradients by definition. And also by definition, the total stress sigma can be related to the deviatoric stress tau through the pressure in the ice. So then with these, we have all these ingredients that allow us to express everything as a system of differential equations modeling ice velocities. But like I mentioned earlier, it's pretty expensive to solve in this form. So to simplify things in the coupled model that Jonathan Kingslake and I developed, we use a frequently used ice sheet model that simplifies these terms by assuming that the ice sheet is a lot longer than it is thick. That's a shallow approximation. This allows us to ignore a lot of the stress gradients, such as the vertical variations in the horizontal shear stress. And also, I choose to simplify things a bit further by making my model a flow line model, so a one-dimensional, a long flow model that assumes there's no horizontal variation in anything in the y direction. So all the y gradients get removed. And this is the case if the ice sheet is particularly wide. And that simplifies things a lot further. And I won't go through the math because this isn't a math class. But after implementing these assumptions and depth integrating, we arrive to what's known as the shallow shelf or shelfy stream approximation, which conveniently can be abbreviated as SSA both ways. And that's what's shown here. This model, it's in all the popular ice sheet modeling packages, and it's been around for a while. And though it's a bit of a jump from the past slide, you can vaguely see how the equations translate. This top equation here, it comes out of the depth integrated mass balance equation. Basically, at any given x along the ice sheet, the change in thickness, dH dt, is due to the accumulation rate A, and also dependent on the speed at which the ice gets advected out of that slice x. Now, this bottom equation here, it comes out of the momentum balance equations and all those assumptions we made earlier. And it shows a balance between the longitudinal stresses over here, the driving stress, which is driven by the slope of the ice sheet. And in the integration step to obtain this depth average equation, we end up adding this basal shear stress boundary term, tau b. And unfortunately, tau b is yet another source of uncertainty. And that's where my focus will be on today. So the reason why tau b carries so much uncertainty is because we need to make assumptions around how ice sheets slide over the ground. It's pretty difficult to observe what the subglacial environment is made of and how the ice interacts with it. Hence, we rely on these empirical sliding law relationships, which relate the basal shear stress experienced by the bottom of the ice sheet to the speed at which the ice flows over it. And sometimes other factors get incorporated into the law as well, such as the effective pressure N, which I'll get to in a bit. Traditionally, and in many ice sheet models, a Weirtman-style power law is used. So this is derived from the idea of a glacier sliding over a hard, bumpy, tombstone-laced bed. And from this concept, Weirtman derives this power law relationship. So an oft-mentioned issue with the Weirtman sliding law is that it doesn't really consider the impacts of subglacial water. But even just intuitively, you can imagine that having like a layer of lubricating water under the ice will impact how the ice slips above. And also, if more water is at the bed, that would increase water pressures, result in more separation between the bed and the ice, and also allow for more slip. So the consideration of water leads to some newer sliding laws being adopted, like this Bud law over here, or a regularized Coulomb law, which I've shown on the right-hand side. And both of these sliding laws, they incorporate the effect of water through the inclusion of an effective pressure variable, N, which is the difference between the ice overburden pressure and the water pressure. And if using the Bud sliding law, we can see that higher water pressures would lead to a lower N. So then for like the same basal shear stress, that would be able to accommodate higher velocities. And then on the right-hand side, this regularized Coulomb law, it essentially regularizes this in the limits of high stresses. And this is informed by the concepts of sliding over cavities or like over saturated till, where there exists a yield stress. And after that point, the stress magnitude remains the same even if velocities continue to increase. So in this instance, when the speeds become fast enough, the right-hand equation becomes tau b equals c times n, behaving like a Coulomb plastic. And also in this instance, in the limits of high N, which implies low water pressures, this would approach a traditional Weirtman law, which still works for hard beds with no water. Um, and in my coupled model, I make use of these two sliding laws as that initial point of coupling between the ice and the hydrology. So in my coupled model setup, the N can be included because I include a hydrology model that calculates it. But then in large scale models used for sea level rise prediction, an active hydrology is sometimes neglected because it can be computationally expensive to incorporate. Instead, many models use inversion techniques with a simple basal friction law, such as a Weirtman law, that doesn't depend on effective pressure. And then what one can do is invert for a spatially varying basal friction coefficient, which is then used to compute the basal shear stress. And in essence, this approach wraps up all the complex processes that may impact basal friction and puts it all into a single parameter. In this case, it'd be like the CW parameter in the Weirtman style power law. And then this unevolving in time parameter can then be used for forward simulations. So here's an example from Arthur et al., who used observed surface velocities to constrain that basal friction parameter. You can see that on the large ice shelves, or on all the ice shelves, as expected, there's no basal friction because it's sliding over water. Um, but then also in like the faster flowing ice streams, like Thwaites over here and the ones feeding into the Ronnie, we can see that there's a much lower basal friction coefficient compared to the surroundings. Now, on the right-hand side, I've included results from Aaron Fucht et al. It's a completely separate independent study that looks at only really at the hydrology. So in this work, they use the current state of the Antarctic ice sheet, so its current geometry, velocity, bed properties, to force a pretty complicated subglacial hydrology model called GLADS. And we can see that there's quite a bit of correlation just visually between their determined effective pressure results and the earlier Arthur et al. Basal friction results. Namely, the ice streams that I pointed out earlier and Thwaites over here, they're all regions with much lower effective pressure. And this kind of implies how when one inverts for these basal friction parameters, they're indirectly including the effect of water. So, quick summary, the subglacial hydrology environment influences the ice dynamics through being able to modulate the flow of ice above it through these sliding laws. The water pressure, it probably also influences, oh, it also influences basal melt and bed deformation as well, which will in turn influence ice dynamics. But then any changes in ice dynamics above the subglacial hydrology system will also change how the drainage system looks and operates, which is all interconnected with water pressure. And that's what creates this bidirectionally coupled system. Obviously, this is connected to even more systems like subglacial aquifers and like the ocean on one end, and all of these are evolving as well. So when we think about these inverted fields of basal friction, it seems maybe not that reasonable to have them be static in time. So in the intercomparison experiments that I described earlier, the one with all the diverging lines representing Antarctica's contribution to sea level rise, a majority of the models use a Weirtman friction law and therefore have this unvarying in time basal friction coefficient. And then the models that do incorporate effective pressure, they usually incorporate it as a simple parameterization, either assuming full hydrostatic connectivity to the ocean or imposing a height above flotation scaling, both of which were relatively ad hoc assumptions that just helped satisfy boundary conditions. And so that's what motivated this work. We wanted to see, from a simple point of view, how an evolving hydrology model coupled with an evolving ice sheet system behaves. And that's what motivates this work that I'm talking about today. And that was published, it was submitted in like 2023, published in 2024 in the cryosphere. And it's this paper that I did with my advisor, Johnny. Excuse me. So the overall goal of this work was to develop a physical understanding of how this coupling may influence ice sheet model predictions. So it's a modeling paper where I combine ice dynamics with subglacial hydrology with these simple coupling components. And I try to explain how the two influence one another from both a steady state and a transient perspective. So in this work, it's a lot simpler than all the points of coupling. And the goal of that simplification was to be able to explain the nature of the coupling. So for the ice component, it's built off the one-dimensional SSA approximation that I described earlier, and that's an approximation that's used by many. For the hydrology component, there's a lot more decisions that needed to be made. Water underneath ice, it can behave in many different ways. There's essentially two broad categories for characterizing these subglacial drainage environments. The first is this inefficient distributed system, like a thin film of water or a system of linked cavities or a layer of water saturated till. And then the second is this efficient channelized drainage system consisting of channels of many different shapes. And quite often it's a mix of all of this. So, like in Greenland, which isn't really the focus of this work, we would expect seasonal transitions between an inefficient system to an efficient system as more meltwater gets to the bed over the course of the melt season. That would create channels that efficiently removes water from the surroundings. And there's been already a lot of good advancements coupling some more complex multi-component hydrology models with an ice sheet to model such seasonal evolution. So work done by Schoof and Hewitt and others a few years ago are great. But for our work, we wanted a simple, explainable, one-dimensional model of hydrology to couple to. So we based our work off of results from previous modeling studies, namely from Christine Dow's group. So this paper suggests that water pressures in Antarctic ice streams, they behave as these consistent high pressure channels. So in this figure, rather than the left-hand side, we expect the subglacial hydrology to resemble more of the right-hand side. And the assumption of these large persistent channels is somewhat backed by observations from those like Drews et al., where they observe these large channels getting carved into the base of ice shelves due to the outflow from these large persistent basal channels under the grounded ice. So in order to model the subglacial channel, we refer to a set of equations known as the Nye-Fowler equations. Um, These equations, along with the mass and momentum conservation equations for ice, they form the entirety of my coupled model. Confusingly, these Nye-Fowler equations are developed for channels that are incised into the ice, so Roethlisberger channels, rather than Nye channels, which are incised into the bedrock. Now, these equations, they've been used previously by those like Andrew Fowler and my advisor, Jonathan Kingslake, and others to model things like glacial outburst floods. And I just want to quickly walk through these terms because they end up being important. The top equation, it describes the evolution of channel size. So the change in channel cross-sectional area, ds dt, it's a balance between the rate of channel opening due to melt in the channel, which is this lowercase m term, and it's balanced with ice creep inwards, which closes the channel. Um, and here with this term, you can see that a higher effective pressure means lower water pressures, which would encourage ice creep inwards and hence closure. And this last term, it's the idea that the flow of ice with the velocity u, it advects the entire drainage system. And this term is pretty important because if we think about the grounding line where the ice is at flotation, that would mean that the water pressures are equivalent to the ice pressures over top, which would mean n equals zero. So then if this term is zero because n equals zero, and we don't include this advection term, uh, if there's non-zero melt, we wouldn't actually find a steady state solution for the channel cross-sectional area. So the inclusion of this advection term, which is dependent on ice velocity, that's our first point of coupling in the ice to hydrology direction. Now, this second equation, this is a mass conservation equation, a conservation of the water mass. So the change in the amount of water due to the change in channel cross-sectional area combined with the inflow and outflow of water at that point, which is the dq dx term, that's dependent on the basal meltwater produced by the channel growth, which is this first term, and additional water sources, which is capital M. And this capital M groups all other sources of water into one subglacial environment, into one term. And just for simplicity, we set that to be a constant. This third equation, it's essentially a momentum balance for the hydrology. So it describes the total hydraulic potential, which is psi plus dn dx, that's required to send the water flowing at a rate q through channel cross-sectional area S. This is derived from a formulation of Manning's equation, which describes turbulent flow in a semicircular pipe, which is what this channel is treated as. So psi, it refers to the basic hydraulic gradient. It describes the hydraulic gradient that arises due to the ice surface and bed slopes, and that drives the flow of water. And this is our second point of coupling in the ice to hydrology direction, because it's really the ice geometry that sets this psi variable. And finally, this last equation, it's an energy balance. It says that the energy used to melt the ice to expand the channel, on the left-hand side, it's equivalent to the energy dissipated by the water flow, which is described by the right-hand side. So now more into the meat of what I did with these equations. With the six equations I described earlier, we have a system of six unknowns. The water flow Q, the effective pressure N, the channel cross-sectional area S, the melt term lowercase m, and the ice thickness H and ice velocity U. But as you can see here, I've rearranged the hydrology equations to remove the term lowercase m. So we just have this five equation system with five unknowns. And these are all in the non-dimensional form. So in non-dimensionalizing, we can gain some insights just by looking at these equations because when we do our non-dimensionalization, all the terms in each equation, they should be around the same order of magnitude unless they have one of these parameter values in front. And I'm just quickly flashing this table. You don't really need to look into it. You can look at the paper for that. But what I do is I calculate all the scale values based on preset scales that are realistic for channel discharge, ice thickness, and glacier length. And then all the other scale terms come out of these really nice looking equations relating these three values with other physical constants. And I just want to use this table to emphasize that the scales are derived from realistic scales and constants. And it's important that we have reasonable values for these scale terms because then we can make inferences about the remaining parameters in the equations, which arise due to the grouping of scale terms in my non-dimensionalization process. So if we look at the beta term in the channel evolution equation, it's always in front of this channel advection term. And we see that by definition, it's the ratio between the hydrologic timescale and the ice timescale. And it also has a much smaller value than all the other terms. So what this tells us is that the timescale for ice dynamics is much larger than that of hydrology. And at least in the context of our model, the hydrology is essentially in this pseudo-steady state. And this is pretty intuitive. It also tells us that this advection term is generally not that important, although we keep it anyways so that we can find that steady state solution as I described earlier. For most of the ice sheet, it doesn't really impact things. Alpha is also relatively small compared to the other terms, and this suggests that in most circumstances, the longitudinal stresses don't have as large an effect as the basal shear stress. And then a small epsilon, that suggests that the gradient in the water flow inside the channel, that is constant because we set m to be a constant. And then delta also turns out to be pretty small. And what this suggests is that most of the water flow in our setup is explained entirely by the basic hydraulic gradient rather than the effective pressure gradient. So then to solve our model, we need to establish the necessary boundary conditions. So for the hydrology component, what we impose is that there's a very small, minuscule amount of water being put in that divide, which is because we need, like one of our assumptions is that the channel is always filled with water. And then at the grounding line, we impose this flotation condition that I mentioned earlier. So the water pressure is equal to the ice overburden pressure at the grounding line because the ice is floating. And that means the effective pressure is zero there. And this assumption has a lot of important implications. For the ice, we assume symmetry at the ice divide, which is the spreading center of an ice sheet. This means that the surface slope and the velocities there are zero. And then at the grounding line, we assume that the ice sheet is connected to an ice shelf. So this bottom equation here says that the longitudinal stresses at the grounding line, they are set by the imbalance between hydrostatic pressures in the ice shelf and the water below it due to the buoyancy of ice. So following some previous work, we include this non-dimensional parameter b for a rudimentary representation of buttressing. So basically, a b equals 1 would imply that the ice shelf is freely floating, so not offering any additional buttressing force. And then to perturb ice sheet retreat, you would just start the simulation by solving a solution with a b value less than 1. Then increasing b to 1 would be equivalent to reducing the buttressing capability of the ice shelf, and that would trigger the retreat. So this method of perturbation is based off a series of experiments from Brondex et al., in which they test out a bunch of different sliding laws. And yeah, you can treat some of our transient experiments almost as an extension of their work. So to actually solve these equations, I use a finite difference approach following Schoof 2007, which was really that paper that established that marine ice sheet instability process that I had described earlier. This model is set up on these one-dimensional grids where the ice velocity and ice thickness are defined on staggered points. The grid itself is split into two sections, a coarse one that covers most of the domain and a fine one near the grounding line. And that keeps the model relatively efficient to run while still resolving um, what ends up being some pretty sharp gradients close to the grounding line. And because the grounding line moves over time, I use this coordinate transformation to stretch the grid as the grounding line shifts. And then with each time step, the grounding line position is updated implicitly based on the flotation condition we established earlier. And then for the hydrology equations, I use a uniform grid with intermediate to high resolution, and it's stretched in the same way as the ice grid. And then during each iteration to solve the system of equations, we're interpolating the effective pressures onto the velocity grid, and then both the velocity and ice thickness values are interpolated back onto the hydrology grid. And then spatial derivatives are taken with center differences, except at the boundaries where there's no set conditions. So there I switch to one-sided differences. And then time derivatives, they're handled with a backwards Euler method. So this is all solved using MATLAB's fsolve function. And this setup is an extension of an ice sheet model that Alex Robel wrote. I used a version from 2021, which is implementing the model that Schoof describes in 2007. So what I did is I added all this additional hydrology component and added in these effective pressure dependent sliding laws. So here's the simplified schematic of the points of coupling I described earlier. And the first part of my work looks at how this coupling, how it appears in a steady state scenario. And I did this really just to see how the features in the along flow line profiles um, look after being coupled. So I run two groups of experiments, S1 and S2. S1, it looks at our bidirectional coupled model in the steady state with the ice geometry influencing the effective pressure, the ice flow, advecting the entire drainage system, and then the water pressure modulating the sliding. S2, on the other hand, is just the hydrology part, and it imposes a preset ice thickness and velocity on a subglacial hydrology, and it doesn't let the water feed back. And these two steady state experiments are really to help me illustrate how the geometry of the ice controls the subglacial hydrology environment. And for ease in interpreting these results, these experiments are all done on a flatbed. And what's nice about looking at things in a steady state is that it makes the system of equations a lot more straightforward to solve. We can just set all our time derivatives to zero and then solve for these five variables of interest. So here's what Q, N, S, H, and U look like, spanning from the ice divide all the way to the grounding line. These are the profiles that are calculated using a regularized Coulomb law with standard parameters. First, looking at the flow rate Q, it's not that interesting of a profile. It starts off near zero at the divide, which is set by our boundary condition, and then it grows nearly linearly all the way to the divide, all the way to the grounding line. And we can see from our scale analysis earlier that with a small epsilon, this basically simplifies it to the gradient in Q being constant, which would mean that Q increases linearly. So it matches with our scale intuition. N and S, they exhibit some more interesting shapes. Notably, N grows continuously as we approach the grounding line, and it reaches this maximum just shy of the grounding line before plunging down to this necessary N equals zero flotation boundary condition that we set. S, on the other hand, it's also gradually growing, hits a bit of a plateau, and then jumps into this really large trumpet-like shape, also right by the grounding line. And I will try to dissect why N and S look like this shortly. In terms of the ice variables, though, we see that the thickness follows the shape that we expect from an ice sheet. We expect the slope to get steeper as we approach the grounding line, and that's what it does. And likewise, with the velocities, they increase as we get closer to the grounding line. Both these profiles, they do exhibit a bit of a taper that is hard to see near the grounding line. This near grounding line zone is pretty important, though, because it's also where we see these really large gradients in N, and also in S. If we do the same experiment with a Bud flow law, we get very similar looking profiles, which are shown in red, though at least in this setup, the near grounding line zone of interest extends a bit further back, like the maximum end is here instead of here. And I did a whole suite of steady state experiments to basically make sure that these characteristic shapes are relatively independent of the parameter assumptions, which they are. And between both these Bud and regularized Coulomb laws, both sliding laws that incorporate effective pressure, I think we can expect the shapes of the hydrology system to broadly follow these curves. So now if we turn to the profiles from our one-way forcing experiment S2, which only looks at the hydrology, these results are shown in this dashed dot line. And here I impose a quadratic shape for the ice sheet and a constant velocity. And when I force these geometries and velocities, I create still the same shapes in the hydrology profiles. Although in this case, because the quadratic profile is always steepening in slope, we see that the near grounding line zone of interest is even closer to the grounding line in this case. But yeah, this is all to really suggest that ice sheet shape is what sets the subglacial hydrology in this model. And now, why are N and S shaped the way they are? It's pretty circular. It's kind of a chicken and egg description. And to try and explain it, I have them plotted side by side here, along with a rearranged version of this momentum balance relationship, now shown in the non-dimensional form. And this relates to the basic hydraulic gradient psi, which is entirely dependent solely on ice geometry, to the effective pressure gradient, and then the water flow Q through channel cross-sectional area S. And I'm going to break down the ice sheet into two regions, one where N is increasing and one where it's not. And this first region, it can be pulled from our scale analysis. So all those parameter terms that I mentioned earlier that were small, if we had set all of those to zero, we can rearrange our equations to get a really simple representation of N. And from the previous plot, we know Q is continuously increasing, and psi, for the most part, is also increasing because the ice sheet is getting steeper. And I'm assuming that the ice sheet slope is a lot more drastic than the bed slope. And this is also illustrated by the blue line in this bottom plot, which is psi. And this, so both of these values increasing means that N is also increasing for the vast majority of the ice sheet. And that's also shown in this top plot. And also following our scale analysis logic, if this delta term was set to zero, this bottom equation would then imply that the flow and cross-sectional area in the channel can be entirely explained solely by the basic hydraulic gradient, which is entirely set by the ice geometry. And this can also be seen in this term plot over here. This yellow line, it really closely tracks that of the blue. And so I placed this red dashed line where this rule begins to fall apart. And to the left of this line in the far field, the simplification holds decently. And from this, we can conclude that the ice sheet shape really wants n to increase almost all the way to the grounding line. Psi, it only really drops once the ice sheet thickness begins to kind of taper and flatten to transition to an ice shelf. But this only happens past that region where the yellow and blue lines diverge. Um, and now you may recall that there is this very important, necessary n equals 0 boundary condition, which is set by the flotation requirement. So when you pair that requirement, that n has to equal 0 at the grounding line, along with the understanding that n is going to be growing for most of the ice sheet as we approach the grounding line, we can easily conclude that there has to be some sort of near field solution that forces n to drop really rapidly close to the grounding line. And that also explains why n has this maximum close to the grounding line. It's a combination of the ice sheet geometry controls and this necessary n equals boundary condition. So how do we allow for n to drop to 0? And that's where this sudden blow up in channel cross-sectional area S comes into play. So if we recall our channel evolution equation, this is now shown on the right after the rearranging to get rid of the melt term and after the non-dimensionalization. Because n equals 0 at the grounding line and because beta is small and because this first term is always positive, that means that the channel wants to grow infinitely large. The reason it's not infinitely large and instead just large, it's because of this small beta term. But yeah, this boundary condition forces S to be large in that region. And we can also think about it as the effective pressure being 0 would imply that the water pressures at the grounding line need to be high to match the ice overburden, and that these higher pressures would promote channel growth. And that kind of is that circular relationship with the effective pressure. So if S is large, if we return to our momentum equation here, that means that this right-hand term will be small. So if we set that one to 0, we can derive this near field solution for n, which is similar to our in a similar fashion to our far field one. And this is similar to some of the boundary layer analysis work that Shuf has done in the past, also work from Tsai et al, and also recently Kazmiracek et al. They do similar work. But when we do this with our coupled model, our near field solution is in fact this full hydrostatic connectivity assumption that's made by a lot of previous work. So one takeaway is that our work lends support to a lot of these models that incorporate this assumption into their ice flow predictions, this assumption of full hydrostatic connectivity near the grounding line. And it supports potentially the usage of these simpler near field and far field simplifications. Basically, we can use the equation in the top for areas far away from the grounding line and the bottom equation for areas close to it. As a caveat, I did not yet explore what the nature of this characteristic length of these regions are. But yeah, looking through these equation terms, it was really only possible to be able to do this term by term look through the simplicity of our setup and also through our understanding of the scaling of the problem. And yeah, that gets us to how n has to have this maximum close to the grounding line because of ice sheet shape and boundary conditions, and that this drop in n is directly tied to and facilitated by this channel cross-sectional area growing large near the grounding line. And to really drive this point home, again, I'm just flashing this plot from my paper. It's not meant to be interpreted in depth. I ran a large series of sensitivity tests where we looked at where this maximum in effective pressure is located. So this is a four-dimensional plot that shows the maximum n position with respect to variations across our physical parameter space. And as we can see, for the most part, these values, so it's relative to the grounding line position. So most of these values are 90% or greater on the way to the grounding line. Only in instances where there's very little accumulation or if the ice is very soft, do we see this region be further back from the grounding line. And in these situations, it's a pretty small glacier that isn't necessarily representative of the marine terminating ice sheets that I'm trying to emulate. And I also just want to mention that I didn't really do this with the intent to compare sliding laws. because others have already done that, like Brondex et al. And I just really want to illustrate that this high end zone is there regardless of sliding law, again, in most circumstances. And that's the first takeaway that I want folks to be able to have, that coupling hydrology with ice dynamics creates a zone of high effective pressures immediately upstream of the grounding line due to the ice sheet geometry controls. This zone of high effective pressure is then brought into agreement with necessary boundary conditions through a sudden increase in channel cross-sectional area. And I'm pretty anchored on this zone of high effective pressure. I realize I've said that quite a few times today, because it leads to the second part of my work, which examines the transient evolution of this coupled system. And before I get into that, let's quickly go back to this issue of ice sheet model initialization. So when one inverts for a static and time basal friction coefficient, they neglect the temporal evolution of all the factors that may influence basal friction, such as hydrology. So what we try to do is we set up these simple transient experiments to highlight why this assumption may impact predictions. And what I do is I set up two experiments or two groups of experiments. The first, which I'll refer to as T1, is our regular coupled model that includes all these points of coupling. What I do is I run it to a steady state past this over-deepened bed. This bed geometry has been used in quite a few modeling studies. It's the Mismit bed shape. Um, and then once it's past this over-deepened bed in a steady state, I reduce the buttressing force to allow the ice sheet to retreat. And for the rest of this talk, I'm just going to focus on the setup with the regularized Coulomb sliding law, just to make the plots a bit easier. But the Bud law, it has the exact same takeaways. So for T2, I use the same initial steady state. But then after I calculate this initial steady state position, which was calculated using a Coulomb sliding law, I calculate what the basal shear stress coefficient would be if it was represented instead with a Weirton power law, essentially taking the effective pressure and putting it into the coefficient for the Weirton law. Then using the spatially variable but temporally fixed coefficient and a Weirton law instead of a Coulomb or Bud law, I can apply the exact same perturbation to the initial state and allow this model to retreat. And this second experiment can be considered our analog to these models that use this inverted field of basal friction without any kind of consideration for hydrology. Um, so once we start the retreat, this is what it looks like at 50 years. The initial position is marked by this thin dotted line up here. The solid curve, this is our T1 experiment with the couple model, and the dash curve is the fixed inverted field result from T2. So this is connected to an ice shelf. So this line is just to kind of cut off where the grounding line is, and the ice shelf is not shown. Uh, so for the solid curve, there's been around 75 kilometers of retreat after the reduction of buttressing after 50 years of simulation. And the hydrology, it's moved with the ice. The zone of high effective pressure still remains behind the grounding line. But on the other hand, we see that when we use our inverted field of static effective pressure, which is given by this dash curve, the T2 experiment retreats up into this region of much higher effective pressures. And the T2 experiment retreats quite a bit less, only around 10 kilometers or so. So now I run it for 250 years, or now if we look at what it looks like at 250 years of simulation, the T1 experiment, the bidirectionally coupled one, it's retreated another 200 kilometers or so, while the ice sheet model without the hydrology has still barely retreated. It's retreated a tiny bit. If I like alternate between the two, you can see it's moved a tiny bit, but not much. And it's still in this zone of high effective pressures. And if we zoom out even further in time, this is what the models look like after 5,000 years of evolution. And this is a slightly different plot that shows the grounding line positions of the two models over time. Still solid is our coupled model, dashed is just the ice. And now our coupled model, it's fully gone through this marine ice sheet instability process that I had discussed earlier. It rapidly retreated across this retrograde slope, hundreds of kilometers, and ends up on this prograde slope portion. On the other hand, the ice sheet model with the inverted friction parameters remains pretty close to where it got stuck. It's still evolving. This isn't like a steady state, but it's still in this area of high N. And to really understand why, um, we can remember that when N gets included in a sliding law, a high N results in a high basal shear stress, so high basal friction. So while the initial condition has this area with a high basal friction, as the ice sheet retreats and thins there, we don't expect that this area remains high in basal friction because the hydrology evolves to follow the ice shape. And that's the case with our coupled model. But when that high friction area does not migrate back due to being fixed as this unvarying in time coefficient, like in our T2 experiment, it inhibits retreat right by the grounding line, and it inhibits it pretty significantly. Um, and this is the second key takeaway coming out of this work, that using a temporally static basal friction parameter can lead to an underestimation of ice sheet retreat due to these higher inferred basal friction coefficients upstream of the grounding line. And to summarize, these are basically the two key takeaways from my foray into modeling. These results, they support the assumption. So as a bonus, they somewhat support the assumption that many ice models already make to try and account for hydrology. This assumption that the hydrologic system has a full hydrostatic connectivity to the ocean near the grounding line. And we show that this only applies close to the grounding line. And I think there's still some room to investigate where exactly it's reasonable to parameterize and in this way. I think Tsai will do some steps into this, and others as well. And just for fun, to take this research a bit further, I came across this paper that I'm not involved with whatsoever. It came out in 2025, and I'm kind of treating it as more or less an informal follow-up to the logic that we had formalized in our work. Here, they use a large ice sheet model built with Elmer ice, along with different flow laws and representations of subglacial hydrology. And for a subset of their models, they assume that the basal friction follows like a Weirtman law and is unchanging in time, like our T2 experiment. But then in the other subset of their models, they implement a parameterization of N near the grounding line, which is really similar to our suggestion of following this full hydrostatic connectivity assumption to the ocean. And what they find when they do this parameterization of N near the grounding line, they find that this incorporation of hydrology, following our suggestion, it can amplify discharge of ice across the entire Antarctic ice sheet threefold, adding an additional 2.2 meters of sea level rise by 2300. So it's great to see that our ideas, which are already a follow-up to a lot of great work by those like Christian Schut, Victor Tsai, Ian Hewitt, Brondex, and many others. It's great to see that our results are already being not directly referenced to, but they're inside these direct applications for sea level rise prediction, and that these newer findings support our result. And I also really want to add one of their figures, just in case one of you thinks it's extreme that our T1 experiment retreated so much while our T2 one did not. This is what they have for their Thwaite simulation. And this top plot is analogous to our T2 experiment, where they use a Weirtman friction law, a fixed basal friction parameter, no account for hydrology, and it barely retreats over their 300 years of simulation. In fact, if we look at the surface slope of the ice sheet, and we can see that this is like where the slope is steepest, and so that will probably be that zone of high effective pressure that I've been going on and on about. On the other hand, when they use this regularized Coulomb law and an approximation for N near the grounding line based on height above flotation, which is another one of those parameterizations that allows for N to drop to zero at the grounding line, they see like 300 kilometers of retreat. So yeah, that's how my research influences sea level rise prediction. And since there's this paper out that has essentially done the main thing that my work was encouraging people to do, what's next for me? So in addition to these takeaways I like people to have, I wanted to also shout out my collaborator, Stacy LaRochelle, who recently started as a professor at UCLA, and she's been doing a lot of great work coupling the couple model that I developed with Johnny with further systems. So she's looking at how it couples with groundwater and subglacial aquifers. And then for myself, I'm working on projects incorporating ice penetrating observations to constrain ice deformation, whether it's on short time scales, like in superglacial lake drainages, or long time scales, like at ice divides. And I'll be at AGU this winter, so if any folks are there, I'd be happy to chat with people about that. Um, but yeah, that's all from me today. Thank you for tuning in and listening. This is the paper that is related to the work. And I'd love to hear any questions or comments.
All right, thanks a lot, George. Are there any questions? There's a lot of clapping. So I guess I was wondering if you can talk about those observations a little bit more. Like, is there something you could use to help um, evaluate your model versus other options or things like that?
Yeah, for sure. I mean, I would always love more observations of like actual channels. I think the Drews et al. Work that I was referring to earlier, they might capture some of the near grounding line shape of the channel, but it'd be cool to see how far inland one can make those observations. Although I understand like they're pretty local features sometimes, so it can be hard to capture. Um, but also, I think it'd be really cool to see if there's like borehole measurements of effective pressures like across an entire flow line. Um, that would better help constrain these models for sure. But yeah, again, I don't think this simplified model that I have necessarily is representative of like a realistic system. I'd refer to like the the Zhao et al. Work, for example, um, for like a better real world prediction.
Any other questions? I guess yeah, I have one more question.
Okay, yeah, cool, cool.
So like in terms of scaling things up, um, uh, like how easy do you think that would be to do? Or I mean,
Well,
I
I
guess
think
that other study you mentioned, they did like a parameterization, but
yeah. So I think at the moment like a full subglacial hydrology model is still too complicated to include. So I know there's been a lot of progress in terms of developing like emulators that can do it. Our work lends some support for these more simple parameterizations that may not necessarily depend on any of the subglacial hydrology variables. So we can arrive at some kind of parameterization that's only dependent on ice dynamics, and then that would be easy to implement. Um, yeah, I'm excited to see. I saw that there was a talk down the road about the ISMIP 7 setup, so I'm really excited to hear that.
yeah, great. Okay, I guess if there are no more questions, we could stop there. All
Cool.
right.
Well, thanks again, everyone.
Yeah.